SwayamPrabha. Digital India. Educated India.
So, in the last class what we did, if you look at the presentation slide, we have found out that in the case of hydrophilic droplet on a hydrophilic substrate which exhibits pinned contact line, you get expressions for, you can write a mass conservation equation, you can find out what is the radial capillary flow, and for calculating that radial capillary flow you need to know H and you need to know Js. So, that is what we are trying to find out. H is written approximating it as a spherical cap in terms of the other quantities. Now, the evaporation flux Js, now we next need to calculate the evaporation flux, and this is very similar to the contact free droplet that we had, right. It depends on whether there are two rate limiting step over here. One is the transfer of mass across the liquid vapor interface. The other one is the diffusive relaxation of the saturated vapor layer in the vicinity of the interface. So, it is like this. So, one is the transfer of mass from there, the other one as it vaporizes there is a layer that forms, okay, where the concentration can be as high as the saturation vapor concentration, right. As soon as the concentration of whatever the solvent is, right, reaches the saturation vapor concentration, this evaporation rate will go down. This is the same thing that happens in the case of your spherical droplet, right. If you have a spherical droplet and you enclose it in a container, right, what will happen that after some time this entire container will be filled up with a saturated vapor. So, this droplet will stop to evaporate. Similar thing happens in the case of a sessile droplet also. What happens is that the sessile droplet, the vapor field that is around the sessile droplet gets saturated. So, unless this gets relaxed, right, relaxed means this has to be diffused out to the ambient, right. So, how the diffusion happens, exactly how we say that it is going to happen in the case of a spherical droplet, right. There is more concentration here, there is less concentration there. So, there will be that Cs minus C infinity by whatever is the length scale of the problem into d, that will be the vapor flux, right. Typically speaking, that is what is going to happen. So, as this vapor relaxes, this area around the droplet is going to become now undersaturated, okay, unsaturated. As a result of that, more evaporation will happen. So, that is one of the rate limiting step, right. So, in most of the cases the diffusive relaxation is the rate limiting step, right. So, you want the vapor, that is saturated vapor layer that is situated around the droplet, around the vicinity of the droplet surface to basically relax out, that means to basically diffuse out, so that you can evaporate more, right. This is the same reason why, for example, if you put a pot of water or if you wash your clothes and put it to dry on a rainy day means on a humid day, right. Do you know that it takes a lot of time for it to basically dry, right. Why does that thing happen? That is because the air that is outside, right, is very humid, is already at full capacity of water vapor, it cannot absorb any more. So, it takes a very long time for that to happen. That means there is no diffusive relaxation of the saturated vapor layer near your cloth. In this case also, near the droplet surface, that vapor layer has to relax, right. Now, in order for the vapor layer to relax, we can always write it like a simple Laplace equation, right. It is a simple Laplace equation, it is basically this. If we write it in one dimension to be equal to 0, right. It is a steady state diffusion problem, it is like a steady state conduction problem also. You can assume it to be like a conduction problem, right. Okay. So, that is equal to 0. This is good when you have time which is more than the diffusive time scale, right, d by r square. You understood the problem. So, this problem assumes that it can be 3D because it is a Laplace operator, even if it is 1D you can write it simply in that particular fashion, right. But there will be boundary conditions which will match it to the interface like we saw in the case of your spherical droplet, right. So, what happens is that along the surface of the drop the vapor has to be equal to the saturation vapor concentration. So, near the vicinity of the drop, or in this case this is the drop, let us say in the vicinity of the droplet, okay, this is always at CS, right, on the other side of the interface, right. Normal to the substrate, the vapor gradient is 0, the vapor gradient is 0 normal to the substrate because of no penetration, right. We are assuming that this vapor do not get absorbed on the surface, okay. And C converges to the free stream concentration far away, that means C goes to C infinity, okay, when R approaches R infinity, something like that, okay. So, these are the cases that we have, right. Now, this boundary value problem, Deegan found that this is identical to a charged conductor if we equate C with the electrostatic potential and J, which is the evaporation flux, with the electric field. That is how Deegan solved this particular problem. So, what he took, he identified an equivalence of this problem. He took that this is a charged conductor, okay, and it is like a charged conductor, okay, where C is like the electrostatic potential, J is like the electric field. The evaporation current in such a solution diverges near the conduction line, contact line of the droplet. That means, near this contact line this value becomes very high, the evaporation flux value becomes very high, okay. So, if you go to the contact line, it just kind of asymptotes like that, got it, very near to the contact line, okay. The evaporation current diverges. So, these are the expressions that Deegan found. He found that Js, which is the evaporation flux, is given by this particular form where alpha is related to the contact angle. Now, you can imagine over here that when R becomes equal to capital R, right, small r becomes equal to capital R, this actually basically blows up, okay, this diverges completely, right, because it is 1 over, is basically 1 over R minus small r lambda, right. So, it basically blows up when R approaches capital R, okay. So, there is significant edge enhancement due to the evaporation, that makes sense because we say that the evaporation rate will be very high. He also showed that this is given in terms of the flux, normal flux multiplied by this additional factor, okay. So, this is the solution that he found for the Js. There is math, so you can do the algebra if you want, but this is basically the expression that you would have. Now, from J we can determine the time dependence. Now that we know J, okay, and it is given in terms of R and T. So, this is the local evaporation rate. We can determine the time dependence of H naught T, that means the height of the apex, right, because height of the apex comes over here. If you look at it, the height of the apex is right there, right, okay. So, the change in volume of the drop must be exactly equal to the evaporation rate, right, that is kind of given. So, if we write the rate of change of mass of the drop in terms of this integral formulation, okay, you get this expression Js and correspondingly H. The velocity of the fluid can now be computed, and from using the values of Js and H you can calculate this particular thing. And if you actually from Deegan showed that if you show that this is the velocity, so it varies from 10, okay, this is the log of the velocity of the solute, that is the particles in this case, versus the distance from the interface, that is r comma capital R. So, as you can see, when this r comma r minus small r, okay, that means when it goes to very low values, right, r comma small r goes to very low values, okay, you have a very high velocity that will try to happen, and and this will progressively go down, okay. So, you can see that the velocity order is of the order of 10 to the power of actually 10 microns per second. This is also has been validated by numerous groups including ours, right, validated by micro PIV or microparticle image velocimetry measurements have confirmed that this is what actually happens, okay. So, you get that this is the variation with respect to the distance from the contact line. So, it is the other way around actually. So, it is the distance from here rather than from here, okay, it is the away from the contact line, that is what we have tried to plot over here, okay. So, you understood that this is how you should actually work out the math of the problem, right. So, you find out J, and J is diverging, and from J and H you can find out what will be the velocity. right. Now, in many of the cases one may not be, so you can now see that the evaporation flux is highly non-uniform across the surface, right. It is very high at the edge, very low at the apex, right. So, it is very unlike the spherical contact free droplets that we dealt with so far, right, where it was very isotropic, correct, and the flow was also diverging, it was going radially outward, right. So, these are the few things that you can get from your hydrophilic droplet. But in many of the cases people were interested, look, I do not want to know that what is the spatial variation of the evaporation flux, okay. Just let me know what is the global evaporation flux, that means what is the total rate of evaporation. I am not interested in knowing that whether evaporation happens more on this side and less from this side, I want an average value, right. That could be the demand of several applications, and that is easy to solve because this evaporation flux we already said it was something like this, right. So, it is very easy that Cs minus C infinity, this is Cs near the surface, C infinity in the far stream, right, and you use the length scale of the droplet as your length scale of the problem here. This is the diffusive flux and this is the diffusion coefficient, mass diffusion coefficient, and or the mass diffusivity, and this is the total area, right. So, just by using this relationship, this is a simple diffusion problem, right. There is vapor over here, this vapor has to diffuse out and that will control what will be the evaporation rate, because we, as we said earlier, that is the rate limiting step that we are looking at in this particular problem, got it, okay. So, what is that? So, D is the water diffusion coefficient, Cs C infinity we already said, R is the droplet radius, A is the droplet surface area, all right. So, so this is the most generic form that you can ever hope to get. However, Popov, okay, gave the following expressions in terms of the contact angle. So, these are kind of like as the contact angle changes, like the contact angle changes, right, because with evaporation the contact angle will change, right, because if it is happening in a CCR mode, the contact angle will change quite a bit, right. So, what he did was that he proposed essentially an expression which is very similar to this, okay, except that now it has a contact angle factor which is f theta. F theta is given by this for contact angle less than 10, okay. So, that is what you have over here. So, for contact angle less than 10, and so this is Cs minus C infinity, okay, that is the same expression that you had before. This is the molecular weight, this is the corresponding radius of the droplet, this is the droplet volume, right, okay. So, he proposed two regimes, one is for less than 10 degree contact angle, this is more than 10 degree contact angle, got it. This is what Popov actually proposed. For a wide range of contact angle you can apply this expression, okay, you can just compute the instantaneous contact angle, plug that instantaneous contact angle in here, calculate what is the global evaporation rate. Remember, this is a global evaporation rate, this does not take into account that whether evaporation is happening more here and less there. This is a global factor that people have actually assumed, okay. So, as you can see, so this is a time marching of the droplet. So, you can see that this is the droplet virtually remains in that constant contact radius kind of a situation, and you see that it slowly evaporates and ultimately goes down. So, there is no droplet there anymore, right. So, this is the evaporation of a particular droplet which exhibits more or less the CCR mode in this case, right. And if you plot the volume curves, you will find that these are the volume curves for the different droplets, okay. Obviously, higher volumes and lower volumes are actually there, okay. So, you can see that these are the kind of volumes that you have. So, 4 microliter volume you start, that takes the longest time, which is very common sense, right, okay. But this expression allows us with the tool to calculate J at any time during the evaporation process, provided you know the contact angle, which in most cases you can measure experimentally or things like that, okay. To calculate the volume, if you see that there is a volume of the drop that is there, okay, the volume of the drop is there, okay. Now, in order to calculate the droplet volume, okay, you assume it to be a spherical shape and the corresponding volume is given like this. These are all expressions, I am not going to go into the details, you can just do the math and find it out, and this is applicable for any contact angle, not just hydrophobic, it is applicable for hydrophilic and hydrophobic because these are the two ranges that we gave in this particular problem. Okay. Now, only dedicated to hydrophobic substrates, it is interesting to see a few more things. Hydrophilic, we said that the flow was very nice, it was radially diverging outward, right. Okay, and we saw the various modes of evaporation, and we saw that the evaporation is maximum at the 3 phase contact line, okay, and low at the apex. However, for hydrophobic droplet situation is very different, right. So, it also undergoes the various modes of evaporation, that is common, same. Okay. The evaporation, however, is maximum at the apex and least at the 3 phase contact line. So, it is maximum here, least here. So, it is the lowest here, this is the maximum here, it is completely reverse, right. In the case of hydrophilic droplets, what we had was that this was the maximum, this was the minimum. In this case, this is the maximum and this is the minimum, got it. Okay. So, instead of a radially outward flow, okay, you can guess what kind of a flow this will create. This will create a toroidal flow, a recirculating toroidal flow like this, okay, due to either due to Marangoni stresses or due to buoyancy. Let us assume that how each of these thing actually happens. So, understood this is completely different from the hydrophilic droplet, got it. In a hydrophilic droplet, this was maximum, that was minimum, in this case it is just inverted, and it also creates a very different flow pattern that you have. Okay. See, if this is for example a sample image of a hydrophobic a droplet evaporating on a hydrophobic substrate, you can see the contact angle is much greater than 90. At one point of time it does become 90 in this particular case, and then it actually evaporates. Okay. Now, why does this thing happens, flow inside this high contact angle droplets? Okay. So, due to the presence of this substrate, okay, what you can see is that there is a wedge like structure, acute angle wedge that is formed near the droplet 3 phase contact line. This is not present in the case of a hydrophilic droplet, there is no edge, it is like an obtuse, right, it is basically like open. This is actually like a wedge, it is exactly like this. It is like a wedge that is created, right. So, what happens is that in this wedge you actually evaporate and fill this space up with water vapor, right. There is a lot of water vapor at saturated condition that actually gets stored in that wedge, right. So, this water vapor is very hard to remove by diffusion, got it. So, this water vapor in this particular region, this region that you see in this wedge region is due to accumulation, and this accumulation is very hard to relax. As a result of that, what happens is that evaporation is locally suppressed in this region, right. However, evaporation in this particular region goes on because it has got no problem in actually diffusing out its vapor. Closer to the interface as you move, closer to the 3 phase contact line, if you move, there is an accumulation of vapor, there is an accumulation length scale, and this accumulation length scale prevents further evaporation from happening, got it. So, there is a local suppression of evaporation. This also leads to a spatial variation in the evaporation flux with the droplet height. So, the maximum evaporation occurs from here, okay, and the lowest evaporation happens from here. As a result of that, you create a temperature and density gradient along the droplet, because here it is evaporating very fast, here it is evaporating slowly. So, naturally locally the temperature will be different, right, in both the cases, right. A substrate which is a droplet which is undergoing very fast evaporation undergoes local cooling, right. It locally the temperature comes down, correct, where on the other hand this is not undergoing that kind of an evaporation. So, locally the temperature will be a little higher, got it. Okay. And as we know that moment this happens, okay, you create a density gradient of some sort, which this one being a little lighter, this one being a little heavier, right, because this is a little hotter, this is a little colder, right. So, as a result of that you immediately create a circulating current like a buoyancy, right. Buoyancy is stable, buoyancy is not there if you have hot on the top, cold at the bottom, right. Here in this case what happens, because there is a lot of evaporation happening over here, locally this temperature, if let us say it is T1 and this is T2. So, T1 is basically marginally lower than T2, marginally, right. As a result of that, what happens is that if you talk about rho 2, rho 2 is marginally higher than rho 1, sorry, rho 1 is marginally higher than rho 2, correct. Because of that, here it is a lighter fluid, here it is a denser fluid, immediately it goes and follows that recirculation pattern, right. This causes the flow to go into a toroidal direction due to buoyancy, as you can see in this picture is very clearly evident that that is what happens. Okay. Now, if the temperature distribution is too high, for example, there could be also buoyancy, there can be also Marangoni related stress. Okay. Marangoni related stress means that higher surface tension will actually pull the fluid, right, towards itself. So, that can also happen in this particular case. So, fluid can be pulled towards the top. Okay. But in this particular case, it is mostly due to the buoyancy effect that is created automatically, right, because of this wedge structure, because here the evaporation flux is low compared to that case. And if you heat the droplet, then situations will be very different as well. Okay. So, this is a very typically very different type of flow compared to the flow that we got in the case of a hydrophilic droplet. Do you see that? That this is more of a recirculating kind of a flow, this is more of a radially outward kind of a flow. Do you see that? So, that should actually ring a bell, and that should actually say that how hydrophobic droplets are very different from hydrophilic droplet, and the evaporation rates are totally different. Okay. Now, as I said, the flow inside the droplet can be also driven by Marangoni stress due to the presence of surface tension gradient instead of density variation. That can also happen. For example, if you heat the droplet from underneath, things like that can happen. Okay. So, Marangoni stress, the velocity that is introduced is given by the variation or the gradient of the surface tension with temperature in the total temperature and the fluid viscosity. Okay. So, the droplet geometry, the thermal conductivity of the drop and the substrate defines the direction of flow. The same diffusion equations are valid for hydrophobic as well as for hydrophilic droplets. There are no changes in that, and the solution is given by Popov. But if you are interested in knowing the insights of what happens within the droplet regarding the flow, this flow field is more recirculating and this flow field is more radially outward moving. Okay. So, this is the big change, okay, and this is like you can study a few of the papers if you have the time. So, including our own work, there are this seminal work that is done by Deegan, which was published in Nature, and there has been some work done by Professor Suresh Garimela, then Semenov's paper, okay, and Popov's paper. You can read all those papers, okay, to get more insights, okay, into the evaporation dynamics. So, here we have what we have done, we have differentiated between an hydrophobic and an hydrophilic droplet. We have looked at how to find out, for example, the flow inside the hydrophobic droplet and the flow inside a hydrophilic droplet, why hydrophilic droplets leads to this coffee stain type of patterns that we see, what are the different evaporation modes, what are the equations that you can write for local evaporation as well as for global evaporation flux, what will be the typical velocity scale inside the hydrophilic droplets. Okay. We have also done measurements where the flow velocity inside hydrophobic droplets have been also measured, is of the same order, is about 10 to 12 microns per second. Okay, and we have seen that how the evaporation flux varies spatially along the length of the interface. So, these things are very important, and this is different from a spherical droplet analysis. Okay. So, spherical droplet analysis, though there are some similarities, like for example, the diffusion dominated thing, if you recall this equation, it was the same. Okay. So, it is like a steady state kind of a problem. There also we said the gas phase was quasi steady and things like that. So, there are some similarities in terms of the basic governing equations, but because of the presence of the substrate, there are some additional problems that it creates. So, the modes of evaporation becomes very important. The evaporation flux becomes highly anisotropic in nature, okay, and that affects your particle transport, your blood, that blood example that we showed, your coffee stain and varieties of other things, mainly happens due to this spatially inhomogeneous evaporation flux. Okay. So, this is the so we will keep this. So, we have done what we are supposed to do in the case of sessile droplet evaporation. Now, we are going to start into one of the important topics in the case of this droplets, okay. And we are going to look at now the droplets and look at how their shapes actually change, okay. So, this was all evaporation and flow, where we assume that the droplet shape does not change, okay, drastically. It is just the shape change that happens due to evaporation. Like for example, in evaporation, in sessile droplets, it either comes down in CCR or CCA mode. There is no corrugation of the interface, okay. There is no breakup of the droplet, right. In the case of spherical droplet analysis also, the work that we showed like Shiriniano and others, we also showed there that the droplet remains spherical, nothing happens to the droplet, right. It is all about the evaporation and the flow within such spherical droplets. Now, in most of the applications, it is not the same anymore, right. In many of the spray applications, like from combustion to pharmaceutical industries, once again like gas turbines, combustion is gas turbine and IC engines. We find gas turbines, IC engines to pharmaceutical industries, we find that spray finds applications in numerous of these processes, right. So, in numerous processes sprays are there, sprays are basically droplets of different kinds, right. So, the interesting feature of a spray is that there the droplets are not always spherical, okay. They actually break, they shatter, they form smaller droplets, they can, this sprays, the droplets can be in the form of ligaments also. So, there are all kinds of dynamics that you can see. If you look at closely this picture over there, you can see that there are ligaments and sheets all around, right. Okay. If you look at, for example, the dispersion studies of a spray, you can see that these droplets need not be spherical all the time, right. Okay. So, sprays are useful, and we need to know how they actually break up, how they actually atomize. So, when you put a spray inside a flow, the spray not only evaporates and evaporates as we have shown, it also breaks up into smaller pieces, okay. So, it is common in the case of biological application, where the sprays are usually like small scale structures, that means it is more quiescent kind of sprays, okay. Whereas the combustion involves sprays which are very large flow rate kind of sprays, which are very complicated, as this diagram over here will show, right. And it can be hot spray and cold spray. Cold spray is basically that you just spray the fluid, okay, and there is mass and momentum transfer, there can be also energy transfer, but it happens at a very low temperature conditions, okay. Whereas hot sprays are in combustion applications, say for example, where we have both mass, momentum, energy transfer at a very high temperature. So, that is what hot sprays are. Combustions are mostly hot spray applications. Spray drying is also a hot spray application. So, some are cold sprays are like sprays which normally dry, naturally dry, like the problems that we did earlier, and there can be examples where the sprays do not dry, okay, and I mean they do not dry at room temperature, they are actually injected into a hot ambient. So, let us look at some of the videos, if these videos play properly. Does not seem to play. Let us see if I can play it from there, okay. So, this is for example a spray, okay, which is coming out, and what we are looking at is basically not droplets anymore, these are basically what we call liquid sheets. We will come to that, what is a liquid sheet, okay. So, this liquid sheet is actually atomizing, as you can see there are bits and pieces which are coming out of that liquid sheet, those are basically droplets of different kinds, right. Now, if we look at this particular application, say for example from the liquid sheet, you can see those tiny fragments that are coming out, those flattering and all those things, you can see those fragments that are coming out. These are ligaments as well as droplets. These droplets need not be of the same spherical size, right, okay. So, that is one thing. And so, if you look at those droplets very carefully, you can see, does they look spherical? No, right. They are liquid, they are blobs of liquid, right, which actually are breaking up, okay, into very small fragments, right, but they are not spherical, right. So, all this work that we said that it has to have spherical shape and other things, there is some inherent assumptions inside that, because these are real life applications, these are coming from the experimental data, and you can clearly see that they are not spherical anymore, The smaller droplets may be spherical, what we are coming out, those bits and pieces that you are coming out over there, they may be spherical, okay, but these major blobs of fluid, they are not spherical, you can clearly see they comes in different shapes and sizes, right. And there are some images like this that you see over there, right, where you can see these small droplets over here, say for example, these droplets, if you look at the cursor, these droplets may be still spherical, but you can see these are ligaments, okay. These are long ligaments, okay, and this is like a bag, this is like a bag of liquid which is actually bursting, okay. These are like different shapes, okay. So, all I am wanting to emphasize over here is that spherical shape of a droplet is not a given thing, okay, it is not given, okay. So, the spherical shape of the droplet as you saw over there or in this particular application, you can clearly see from the examples, from the violent shedding, that they cannot be, need not be spherical. There are a lot of ligaments that you see, right. If you watch the video very closely like a movie, okay, you can see clearly that this is what is happening, right. So, and this happens when you actually put it in a high speed flow, and if you look at the close up, you can very clearly see that they, wow, these droplets are no way they are spherical, they are doing this bag and all these types of breakup, right, correct. Okay. So, that is becomes then a very important parameter over here. Okay. So, hot sprays as we saw are due to that, and these are the some images which shows that the sprays need not be spherical. So, and this will be the last slide for this particular lecture. What we will show over here is that the spray formation is basically a complex process, right. So, as we showed that there is usually there is a liquid sheet or a jet, and this liquid sheet then breaks up and forms all these ligaments that we showed in the previous video, okay. And these ligaments then breaks up and forms numerous droplets. This parent droplet once again deforms and breaks up into daughter droplets, right, at a far downstream location, right. So, first one where the sheet breakup happens is called the primary atomization zone, right over there. This is the primary atomization zone, right, where the sheet is actually breaking up, and this is called the secondary atomization zone where the droplets actually break up, and droplets cannot break up without changing their shape, right, they cannot remain spherical, right. So, this is secondary atomization, this is primary atomization zone, and there are basically it usually involves liquid sheet, ligaments, formation of parent droplets and formation of daughter droplets, okay. So, there are numerous examples like this, like for example, here you can clearly see a ligament that is breaking up. Do you see that? This is a ligament that is actually breaking up, correct. Okay. There are all these ligaments of different kinds that you see, right, they are actually breaking up, okay. And once this ligament, you can also see ligaments like that over here, ligaments like that over there, right, okay. And individual droplets can also break up, okay, due to this bag mode. This droplet can actually break up into further droplets which will be more in the secondary atomization kind of a zone. Whatever it is, my point is very simple, is that the droplets actually breaks up, okay, and they cannot break up without exhibiting a exhibiting a non-spherical kind of a shape, okay. And there are different parameters of interest over here, the droplet size, the droplet dispersion, the spatial uniformity, the nozzle through which these droplets are coming out, the droplet effects, that means one droplet sees another droplet in its neighborhood, what does it do, okay. So, primary breakup will define the global structure, the primary atomization is influenced by the nozzle, and there are other parameters, not just the nozzles, the flow field and other parameters. Secondary atomization involves basically the flow and the droplet interaction. So, these are like droplets which interacts with the flow field, like this is a droplet, there is a high velocity flow over it and this droplet deforms and breaks up. So, that will be like secondary atomization, okay. And then these droplets will undergo evaporation, mixing, etc. Normally the atomization process is very fast, very quick compared to the evaporation process. So, you can take that evaporation only starts to happen after the droplets have substantially reduced in size. There is evaporation that continues to happen always, but if you talk about the dominance of the scales, atomization happens at a much earlier time, Okay. So, what we are going to talk about in the next hour or so, in the next 2 lectures, is basically the precursor events basically to evaporation. So, evaporation will not be important, we are not going to consider evaporation that much, but we are going to consider that this is the evaporation that actually evaporation only happens after atomization is complete and you get droplets of sufficiently small sizes, right. And there, this is of course a field in its own, there are a lot of interaction parameters, there are a lot of evaporation mixing and all of these things happens, makes it an extremely complicated subject, but we have shown some examples where it is very clear that why droplet atomization is important, okay, because that is what happens in real life in each and every process that you look at. You cannot just consider the droplets which are here, which are very stable, does not undergo any breakup. You have to know what is happening there before you can understand what is happening here. Okay. So, that is very important. So, in the next class what we are going to do is that we are going to look at the atomization process in a little bit more details and study a couple of models, which is basically called the tab model and the wave breakup model, and we will see that how the droplets actually deforms and atomizes. We are not going to do primary atomization that much, we will do a little bit, but we are not going to do, because that itself is very complicated and it is not properly resolved, but we are going to give you a heuristic understanding of what is going on. Thank you.